Hi, welcome to AgileTD After Work. Today, we're very happy we have Dr. Elmar Jürgens with us. That's very nice. And we are looking forward to hear him. But first, we invite him to the front so that we can talk a little bit. Hey, Elmar, how are you?
Hi, I'm good. Thanks. Thanks for having me.
Yeah, welcome. So tell me, who are you?
I'm Elmar. I'm one of the founders of CQSE. I did my PhD on software quality analysis because you mentioned me as a doctor. And I'm interested in how we can find more bugs in less time. That's the stuff I've been working on in the last 15 years.
Okay, that's very nice. So you are going to talk about that today, right?
Yes.
So, and enjoy the audience. I will be in the back, so I let you in the front. So I will control everything here, so no worries about that. And of course, if you have questions, just write the question down and link it in, and I will tell that to Elma. Okay, so enjoy.
Perfect.
Okay, see you later.
Thank you. Thank you all for coming. Welcome to my presentation. We have to test more and more functionality in less and less time because successful software grows from release to release. We always keep adding new functionality. We hardly ever remove features. But paradoxically, we don't get more time to test more functionality, but less because release cycles are getting shorter and shorter. And I think we can only manage this in the long term as a discipline if our testing becomes more specific to those areas where bugs are very likely to be in the software. And this is where my presentation comes in today. I want to present test selection approaches. Different approaches that help us select which tests make the most sense now to not always run all the tests. And as the title suggests already, I will look at approaches that use AI to find the tests that make the most sense now. But I won't limit myself to AI-based approaches because AI is not a goal in itself. It only makes sense using it if it brings something to the table that's useful. So I will also look at old school approaches that don't use AI but solve the same problem. Before I start, please ask questions directly. Don't wait until the end. And it needs not be a well-articulated question. It's fine if it's your own experiences or skepticism or even doubt. Testing is different in different organizations. So if I have examples that don't match your context, feel free to interrupt me. Maybe I have another example that works better. And before I start with a specific test selection or test suggestion approaches, I want to start with a metaphor to show where other approaches, where other fields are already successful in selecting specific test cases that you all know from outside of work, which is X-ray pictures. This is an X-ray picture of my right kneecap, which I unfortunately broke in an accident a couple of years ago. This is the kneecap. The bright lines are the steel wires that wrap together the pieces of bone, and the small wires, the small lines here are the clamps that close the scar. So why do I have that here as an example? Obviously, I don't mean the accident or the surgery that took place the same day. What I'm referring to is the quality assurance that took place 2 weeks later when I was sent to a doctor. And what I found very interesting was that the doctor did not take my temperature. He did not take a blood sample and analyze it. He didn't even ask me where the pain was. Instead, he only took this picture to see if the change that the surgeon performed to my system matched his expectations. So in testing terminology, the doctor did not retest all. He did not run all the analyses that he could have done on my body or me as a patient, but instead he did a specific analysis targeted at the change that was performed to see if there are any problems left or introduced by that change. And today I want to look at approaches that have a similar idea, that look at the changes that were performed to select the test cases that are most likely to find bugs introduced through that change. Some background on me so that you know where those experiences come from. We already had a bit of that in the introduction. I'm a computer scientist. I studied computer science in Munich. This is how I looked when I finished my studies and started the PhD. I did my PhD in software quality analysis. This is how I looked when I finished the PhD. And then I co-founded CQSE, a company that does software quality analysis and also works in the area I'm presenting. I've been told that this slide mostly shows that there was always enough food available during my PhD. But the point I want to make is different. I still look at this topic from both perspectives. As a postdoctoral researcher, I'm interested in what's relevant to measure. Because unfortunately, we often measure what's easy to measure, but not what's relevant to know, especially now in the AI hype cycle. So I really want to know, is it useful to apply a certain approach? And we do a lot of bachelor's and master's theses, and we have a couple of PhD students in our company that work on this. And as a founder, I'm interested in impact. Just by stepping on the scales each morning, I don't lose any weight. And just by installing some tool that runs every night, nothing improves. So as a founder, I'm interested in impact and in seeing if the analyses are really applicable in practice. So the experiences I have are not only from me in this presentation, but also from the 65 colleagues I have. Most of them also computer scientists, and 20-something have a PhD in software quality analysis. So we're really focused on this area. And for full disclosure, the company I co-founded builds a tool called TeamScale that implements some of the analysis I present today, but I won't talk about the tool at all. I just want you to know that this is my background. So if you ask me what I think the best tool is, I'm obviously biased. Last slide on background. This is some of the companies we work for. And the key point I want to send is that even though obviously a system running in a bank that's written in COBOL and is executed on mainframe looks very different than a system running in a car or on a mobile phone. But if we take a step back, then all those systems face the challenge that there's more and more functionality we need to test in less and less time. So that my key message here is that the problem and the approaches that work to solve it are not dependent on a single programming language or organization or domain, but we see them applicable across the board, across very different organizations and systems. So, many of the teams we work with fortunately have a lot of automated test cases or a lot of manual test cases that they want to execute. This is different than 20 years ago when I started in this domain. Typically there was a very low level of test automation. Now, a lot of the teams we work with have very many tests. Unfortunately, it takes too long to always execute all the tests in the available time frame. So one idea to still have very quick test feedback, even though the test takes very long, is to only execute a part of the test suite, but select this part, the subset, in such a way that the small amount of tests finds a large amount of the bugs that the entire test suite finds. Let me illustrate this. Imagine every rectangle here, every gray rectangle is a test case, and the green area represents which part of the system this test case tests. And imagine we executed all those test cases, and some of them failed, revealing bugs, and represented here by the white X on red background. Now, unfortunately, as you know, there's no easy one-to-one relationship between failing test cases and bugs. Instead, often a single bug makes many test cases fail. And I've symbolized that through the color of the bug icon here. So these 4 test cases reveal the blue bug, these 2 reveal the orange bug, and this single test case reveals the purple bug. And if we select the test case in a clever way, if we select the test set we execute in a clever way, we could, for example, end up with the test on the left-hand side. And we can't guarantee that we find all the failing test cases. But if we find one test case that reveals a bug, then this is enough for that bug. So in this case, we found 2 of the 3 bugs because This test case reveals the orange bug, and these test cases reveal the blue bug, but we didn't select the purple bug. But in many scenarios, this is already sufficient because we know there's still bugs in the system. And in this case, we could halt all more expensive testing or deployment and fix those bugs first. And in my presentation, I want to look at 2 different use cases that are applicable in different areas of development and testing, where test suggestions can help us speed up our testing. The first one is during a quality gate. And I learned this from our customers, especially in areas where there's hardware involved or end-to-end tests take a very long time. I learned that a long test run is a very expensive resource on its own. We have customers that test their software with machines, with hardware, and it takes over 400 hours to run the entire test suite. So if there's a bug in this test suite, in the software, that makes a lot of test cases fail, then this single bug ruins the entire test execution, because the many failures from this single bug hide any other bugs that are in there. So these customers have an acceptance test suite or a smoke test suite that the software needs to pass in the quality gate to be allowed onto the expensive test run. And what I want to present now is a test suggestion approach that tells us what are the best tests for such an acceptance test suite. How can we make the most of the available time to find out if the software is good enough to be allowed into our acceptance test suite, and if the software is good enough to be allowed onto the expensive test run. So we don't know anything about the changes in the software, but we still want to find a small amount of test cases that finds a large amount of the bugs. And how can that work? That works because most software test suites are very redundant. And if we select the subset of tests in a clever way, we get rid of the redundancy and still find most of the bugs in a small amount of time. And I want to use a paint program called Pixelitor to illustrate how this redundancy feels. This is a screenshot of Pixelitor. Pixelitor is an open source Java program, a bit like MS Paint or a very simple version of Photoshop. And now I want to use the code coverage of the individual tests to show you where the redundancy is. And let me just explain what I mean by code coverage so that we are all on the same page. This is a Java method from Pixelitor. I don't expect you to read it now. But you see that the lines in the background, all the lines that can be executed, are either green or red. And green means this line was executed when the tests were run, and red means the line was not executed when the tests were run. And this information is called code coverage, and it's produced by so-called code coverage profilers. Software that runs in the background, you'd still do the testing as you did before, and code coverage profiling is typically used in automated unit tests, but the code coverage profiler does not care what type of test it profiles. We use it also for automated end-to-end tests or UI tests, and we also use it for manual tests. So code coverage profiling is useful to see what was actually executed during testing. And now let's use that coverage information to look at how tests in the test suite of Pixelitor relate to each other. And for that, I quickly want to introduce this visualization that helps us to look at the entire code base at once. This is a tree map of the source code of Pixelitor. Every rectangle represents a source code component, and the bigger the rectangle, the bigger the corresponding component in lines of code. And now let's zoom in. This is the source code files, and this is the source code methods of Pixelitor. And it still holds the bigger a method, the bigger the corresponding, the bigger a rectangle, the bigger the corresponding method in lines of code. And now we've got all the pieces together to look at the redundancy in the test suite. What we now do is we execute the end-to-end test suite of Pixelitor. Each test case after each other, and we look at the coverage. And here you see in green all the methods that the first test case covers. So when we run the first test case, which is called test Gaussian blur, the green methods are executed and the gray methods are not executed. And how can we interpret this? If we enter a bug in a green method, there's a certain probability that this test will reveal it because it runs through that method. And it could be that it tests something there that reveals a bug, or that the bug crashes the test case if it passes through there. If we enter a bug in a gray method, there's zero probability that this test case will reveal that bug because it doesn't traverse it. So this is the first test case. This is the method it runs through. Now, the second test case in the suite is called test motion blur. And now green are methods that are covered for the first time during this text execution by this test. And blue are methods that are covered by the motion blur, but that were previously covered already by the Gaussian blur. So we see there's a lot of redundancy, a lot of methods that were tested already and that are tested again. The third test in the test suite is called test lens blur. The fourth test is called test smart blur. And I think you know already what I'm aiming at. You see there's a lot of blue code that was tested for the second, third, or fourth time by those tests. And there's hardly any green code left that was tested for the first time. So if we take a step back and zoom out and look at those test tree maps, I've piled up the green methods, the code that gets covered for the first time during that test execution, on the right-hand side. And you see that there's a saturation. There's hardly any new code tested in the first test. And empirically, we know that the code that gets traversed by several tests, either, if there's a bug in there, either all the tests find it or none of the tests find it. So from an efficiency perspective, the first test we execute that runs through a piece of code, that adds a lot of fault-finding capability, but the remaining ones that runs through there, not so much. So it's inefficient to run all those tests from one cluster if we want to find many bugs quickly. So there's a research area called test prioritization that has for decades looked at the question, how can we improve the ordering of tests to find bugs more quickly during a test execution? And we've implemented very many prioritization approaches. And the best one we found always selects that test case then next, that per second of test execution covers the most lines of code that were not yet executed. So what happens if we run this approach to reorder the tests in Pixelitor? Then we get this sequence. We start with a test called create and modify selection. And because this is the first test execution, everything is green. The second one is called test change view settings. The third one is called test second layer. The fourth one is called test save image. And it's not important what they do exactly, but you hear it's not blur, 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 but very different functionality in each test. There is still some blue code, which is typical for end-to-end tests because there's some software stack that gets traversed by every single end-to-end test, but there's a lot of green code still. So if we take a step out, you see that the same number of test cases, 4 that took approximately the same amount of time, covers a lot more code if you compare the amount of rectangles in green on this side to these ones. So let's move from this illustrative example of the small open source paint program to a real world system from a customer. This picture, this chart is from a software system in the medical domain. It's dialysis software. And the test suite, the automated test suite runs for 48 hours to execute the whole test suite. And on the y-axis, you see how the coverage builds up. And what you see here is a lot of plateaus, like stairs and steps in a stairway. And each plateau is a cluster of very similar test cases, much like the blurs in the Pixelito example. And if we run the sequence optimization on this test suite, we transform this chart into this chart, where you see that the coverage increases way more quickly. And now the key idea is, if we cut off the test execution time here and only execute like the first several percent of the test suite, then in the optimized version at arbitrary cutoff point 8% of the time, we get almost 100% of the coverage that the entire suite finds. But had we cut off here in the default sequence, we would be below 20% of the code that got covered in the default sequence of the tests. And now I've so far only argued about test coverage, and that we use test coverage as a metric that we optimize during the reordering of the tests. But what we're really after, perfect, a question. Let me just finish that thought, and then I pick up the question. What we're really after is fault finding capability. So instead of looking at coverage only, we did a lot of empirical research to see, does this really translate into finding more bugs faster? And our PhD students and master students looked at open source software and historic bugs, and also used mutation testing to insert thousands of artificial bugs, where we broke pieces of code to see if the tests found them. And we saw that on average, over the different systems, if we use 6% of the time it takes to execute the entire test suite, on average, we find 80% of the bugs that the entire test suite catches. And in 11% of the time, we find 90% of the bugs that the entire test suite catches. And last slide on that approach, we have one customer called BVK, Bayerische Versorgungskammer. And they had a test suite that runs for 20 hours. So they executed that, I think, every weekend. And we used 5% of the 20 hours, which is 1 hour, and computed the best tests to run in that hour. And they are now performed every 2 hours. And still, on the weekend, they run the long test suite. And this gives us a very good experimental setup to see how many bugs slip through. And they told us that in the 5% of time, they find 70% of the bugs, and 30% slip through and are reported on the weekends, just like before. But for 70% of the bugs, they get much faster feedback times now. So I saw there was a question. There is it. How do you distinguish test failures that are caused by application changes that occurred since the last run of these tests, and test cases that failed because of actual bugs? Excellent question, Dennis. And the answer is we don't. So our goal is to find failing test cases, because I think independent of whether the test failure is caused by an application change that requires a refactoring of the test, or a fix in the test case, or if the test failure is caused by a bug that requires a bug fix, it's better to know early that the test will fail than know late. Because if I introduce a bug, or if I introduce a change to the application that breaks the test case, if the test case fails in 1 or 2 hours, it's very easy for me to remember which change I did that broke this test case. So it's rather easy to figure out what did this. If the test tells me in 3 months, it's so much harder, because A, I have forgotten what I've done 3 months ago. I'm not 20 anymore. I can't remember that. And second, so many more things happened in the 3 months that could be the culprit of the failing test case. And so it's much more work to figure out what the problem was. So I think for both cases, if it's a change to the application that requires a refactoring or a fix in the test case, or if it's a bug that requires a fix in the source code, it's good if you have much shorter feedback cycles for the test suite. And this approach can help in both cases. Thank you for the question. Please let me know if the answer was helpful, or if not, please ask a follow-up question that helps me understand the question better. And thank you for the question. It really makes it more fun for me if there's questions. So this approach that uses test case specific coverage to select the test suites to execute more frequently works very well. But, and that's a big but, we need test coverage. We need test case specific test coverage. And it's a lot of effort to collect that, because we need to wire the automated test case with a test coverage profiler and execute that in isolation. We do that with some customers and in some teams, but it's a lot of effort. And typically it takes several months to collect that data. So in the last years, we've asked ourselves, can't we do a similar optimization without test case specific code coverage? Because then it would be much easier to apply. And the key idea is, what we really want to do is break up those clusters of similar test cases to get such an ordering. And if I gave you the textual test cases, if it's manual test cases, the natural language description of the test cases, or if it's automated test cases, the code of the automated test case, then as a human, you could look at them and decide, are they very similar or are they not so similar? By looking at many test cases, you get a feeling for the similarity. And we've, in the last years, implemented a lot of approaches that work on different similarity measures for test cases to get a similar result without coverage. And this is where AI comes in, because we've tried approaches with AI and without AI. And let me first explain how the approaches work in principle, and then where AI comes in. Because what we do is we transform the test cases into some vector space, some highly dimensional vector space, very many dimensions. But for the sake of simplicity on the slides, I've presented it here as only 2 dimensions. And every single test case is one dot in this vector space. And there's very many different ways of transforming test cases into vectors. And then we can measure some distance between test cases. And then if we have the vectors and the distances, we can simply cluster, we can simply compute the sequence of tests by starting with one test case, for example, the fastest one, and then selecting as the second test that test case that's the furthest away from the first test case. Because then the probability that they are on this same cluster, that we have one blur and then select a second blur, for example, is very low. And then the third test case we select is the one that's the furthest away from the 2 that were already selected. The next one is the one that was the furthest away from the 3 that were previously selected, and so on. And now the key question is, what's a good way to transform test cases into vectors and have a distance between them that's actually meaningful and has a good result for this problem? And the answer turns out that large language models are perfect for this, because they don't work on words directly, but transform words and sentences into so-called embeddings. They embed them into some vector space and then compute on them. And the nice property of embeddings of large language models is that they preserve some semantic properties. For example, here are embeddings for 4 words: man, woman, king, queen. And there's a similar distance between man and woman and between king and queen. So this is a certain notion that there's some semantic preservation. And this is really useful because this notion helps us break down the clusters in test suites without needing test case specific coverage. So what we've done to see how well this works is we ran the same experiments on the same systems. And before we saw that to find 90% of the bugs, we need 11% of the time. And with this approach, we find 90% of the bugs in 13% of the time. So it's a little worse. It's 2 percentage points worse than the test case specific coverage based approach, but it's so much easier to apply. Just to put this into context, we had a customer last year that worked with us with the Pareto optimization approach, and it took us 6 months to capture test case specific coverage. We have another customer that started last week with AI test clustering. They started on Tuesday, and on Thursday they had the clustering done. So this is really so much easier. I'm always joking, I would probably only have half the amount of gray hair if I had known this approach, if we had thought about this approach earlier than the test case specific coverage one. I see there's a question from Mohammed. How are you quantifying test selection impact across shorter release cycles? How are you quantifying test selection impact across shorter release cycles? I hope I understand the question correctly. So what we do is we first determine what's the time budget for the test. For example, 5%, 8%, 1%, depends a lot on how many tests you have, how long they take, and how much time you have available. And then we select those tests that produce the best coverage for the available time frame. I hope this answers the question. Otherwise, please ask again if I misunderstood the question. Mohammed, thanks a lot for the question. But it's also a good segue into the second part of my presentation, which talks about how to do this during continuous integration, because maybe your question was also aimed into that direction. Because remember, so far, we were talking about how to optimize test selection for a quality gate. And in the quality gate, we didn't know what changed since the last time we ran the test. This is different in continuous integration. In continuous integration, we often run the tests every hour or every couple of hours or every branch merge. And we know we can compute at least what changed in the code base since the last time we ran the test. And this allows us to optimize even further. And I have an example from our own development to illustrate this and to give you a feeling how much data these optimization approaches have available and why they can do better than the ones I've so far presented. This is a tree map of our own analysis tool. Every rectangle is a method. This is 40 to 50,000 methods of our code base. And what you see here in orange and red is the code changes performed for a single ticket. To be more specific, since we do static code analysis, among other things, whenever a programming language changes that we analyze, we need to adapt our scanners and parsers and semantic analysis so that it still works with a new version of the programming language. And a couple of years ago, Java received closures as a language feature. And this is all the changes to our code base that were performed by Andreas back then, so that Java's closures can be understood by our tool. And this orange is code that was there before and modified, and red is code that was written new. And it's distributed across the code base because it touches very many parts of our tool. And now what I want to do is I want to start a time-lapse video of our automated test coverage. Every second we run 30 tests. All the methods that are executed by one test are depicted in white, and then they fade to green. And here you see how the coverage builds up slowly. You see there's some areas that are tested by very many tests. There are some areas that are tested in isolation. It's a bit like a weather radar where we see how the test coverage builds up. The important message is when something gets tested, it's first white and then it fades to green. And I think the point is there. Let me stop the recording now. We see a lot of the code that was orange and red before we started the tests is still orange and red. I didn't run all the tests, but back then we had roughly 5,000 automated tests. And of those 5,000, 4 ran through the changes from this ticket. Not 4,000, only 4. But in this case, only those 4 test cases can find bugs that were introduced through these changes. all the 4,996 test cases that do not run through any of those changes, they cannot find a bug introduced by these changes because they don't run through that. And the key idea of test impact analysis is to throw out all the tests that don't run through modified code and then perform the sequence reordering we saw before, and then only execute the impacted tests in the correct order. You see, I always use the same cutoff point here. Test impact analysis requires 2% of the time only to find 90% of the bugs that the entire test suite finds. So this is much better. This is the best approach we know. But again, it requires test case specific coverage. So it takes several months to get the information to get this running. But because it's a very effective approach, there's some cases where it makes a lot of sense. For example, our customer Dolby, who you know from your last cinema visit when they had very good sound, they have the challenge that they have a very large parameter space because they need to test their software for different parameter configuration. And this blows up the number of test cases. And they use this test impact analysis approach in their continuous integration and get this into the 10 minutes that are available. Mohammed, maybe this is a good illustration of your question also, because here they decided we don't want to spend more than 10 minutes during continuous integration for every single commit. Otherwise, it slows down feedback cycles too much. So this is how they decided to spend a 10-minute window. And sometimes test impact analysis selects less than 10 minutes, then it's faster. And if it selects more, then it's cut at 10 minutes. So this was, again, the old world version that requires test case specific coverage. And again, the question for the last approach is, can't we do this without test coverage as well? And a couple of years ago, there was a paper from Facebook that was called Predictive Test Selection. That was the first widely regarded approach that used AI to answer this question without test coverage. And some tools, there was a startup called Launchable that implemented that approach, and there's also Gradle test case selection that does that. So the key idea is this. Imagine in the past we changed file A and ran all the tests, and test T failed. And at a later point, we changed file B and ran all the tests, and then test U failed. If we have a lot of data on which files changed and which tests failed, then we can feed that into AI and then have it predict which tests we should execute if certain files change. So if at a later point, again, file A and B changes, then this AI could present us with the prediction that we should execute T and U because they failed in the past when those files changed. It's a bit more involved. It works with a lot of data. And what we did is we did a bachelor thesis at the TU Munich here to see how well this works. And before here, the approaches for the results for predictive test selection are here in the middle. But I first want to explain how to read these charts before I reveal how well predictive test selection works. So our left baseline is simply running all the tests. And the question we ask here is, how long does it take on average across very many systems and very many bugs? How long does it take on average until the first test case fails if the system contains a bug? And if we run all the test cases in the default order, then in the systems we studied, on average, the median is a bit less than 20% of the time it takes to execute the entire test suite. On the right, you see the test impact analysis results, and it's so fast that it's hardly visible. It also has this box plot, but it's all in one line. So on average, it's less than 1% of the time it takes, in this case, where there's bugs. And now, how does predictive test selection score? That's here. And how do we read this? The median point is a little bit below the retest all. So statistically, we can do a significance test, and we see that statistically predictive test selection is better than retest all, because it's a slightly different, a bit below here, and this one's below here, and so on. But in practice, the difference is so small that it doesn't really change anything. So the result we took away here is it's not useful, unfortunately, because it's such a promising approach. And the key problem is this approach requires a lot of test execution data to work. So the more fine-grained the tests are, like unit tests that test a single method only, the better this approach can learn the correspondence between test cases and code changes. Unfortunately, the higher up the test pyramid you go, the more we go from unit tests to component tests to UI tests to end-to-end tests, the worse this approach gets, because there's way more code that gets executed by a single test, and test execution is much less frequent. So harder learning problem with less data. I think that machine learner can't be blamed, but there's just not enough data to learn that from for the interesting problem cases in practice. So unfortunately, after this bachelor thesis, we decided not to pursue this approach. So what we looked at instead was search engine technology. Because imagine we work on a banking system, and as testers or test managers, we get the information that there was a ticket considering login, accounting, and search that was modified. Or we are given that information through some means, maybe through the tickets, maybe through bug reports, maybe through the release notes, whatever. What we would then do is search in our test cases which test cases are for login, which are for accounting, which are for search, and so on. And then select those. And this is a problem that search engines have worked at for a long time already. And it's like very self-evident for us that a search engine like Google or others is very good at that. And so what we did is we used that technology and put that to test case selection. So how does that work? We take all the test cases, be that manual tests or automated tests, and they are in the web search metaphor, the web pages, the documents that we index over. And then we take the code change, and not only the code lines that changed, but also the context, like the code above and below. And if we can get it, the tickets, we can use any text that describes a change as input. And we construct that to a query. And then we select those test cases that match the query the best. So let me give you an example. There's an open source Java system called DigiBank. That's an online banking application. And this is code from the DigiBank. And there's a method called transfer that transfers money between different accounts. And imagine we made a change to that method. And there's several identifiers in here, like method name or log statement, or here the name of the attribute we set. And the information retrieval or search engine technology, it extracts the characteristic identifiers. And now if we look at test code from a unit test, we see it selects the unit test that has similar characteristic identifiers. Or here's a cucumber test that has that's selected on the basis of those identifiers. Here's a robot framework test that works similarly. And here's even a manual test where also those characteristic identifiers are selected from. It's a simplified test case. It's more complex. It also works if there's not the same combination of identifiers, but I thought this example was more tangible than a more complex one. So you've seen that slide already for the other approaches. The approach I just outlined is something we call similarity scoring. And again, we've had our bachelor and master students run the same experiments on similar systems. And here, on average, we see that in 4% of the time it takes to execute the entire test suite, we find 90% of the bugs that the entire test suite can find. So now we've seen 4 different approaches. 2 that use test case specific coverage. In the quality gate use case, that was Pareto analysis. For the continuous integration, that was test impact analysis. And 2 that don't need test case specific coverage. AI clustering and equality gate and information retrieval or similarity scoring for the continuous integration use case. And we take 11%, 2%, 13%, or 4% of the time to find 90% of the bugs. And the more information we add, if we add change information, if we add test coverage information, the better it gets. But which is the approach that we think is the best to start for most teams? Surprisingly, it's not the best one. Instead, our experience is that even though AI test clustering is the worst in the sense that it finds the least amount of bugs in the available time or takes the most time to find 90% of the bugs, it's so much easier to get to run that this is the approach that we think is the best suitable for most of the teams. So this concludes the part of my talk about test selection or test suggestions. I have a bit of a bonus track because test selection cannot help us if there are no tests that cover a certain part of the code. And I want to spend 5 more minutes on what we can do to see if we miss the tests and that we need more tests. But before I go into that, are there any questions that concern the test selection approaches? Then now would be a good time to ask them. And Mohammed, did I answer your question correctly? Doesn't look like it. If there's further questions, please just put them in the chat. So, what if we lack tests for a critical change? What I want to quickly outline is an analysis called test gap analysis that shows us changes that were not tested. And the idea is very simple. We extract change information from the version control system and use test coverage information to see which changes were not tested. And I have an example from Munich Re, the world's largest reinsurance company. And I have the permission to show this, but I have to say this was back then, and now it's obviously much better. So what do we see here? This is a business information system, 1.5 million lines of C# code. Gray means not changed since the last release. Orange and red is modified in new functionality. 30 people worked on for 6 months on these changes. And if I was the test manager, I would try to make sure that we test the right part here especially thoroughly. Second piece is test coverage. Green means executed during testing. Gray means not executed during testing. And this is the aggregated information from automated unit tests, automated end-to-end tests, manual regression tests, and manual explorative tests from 2 weeks of testing. Now, how does this look if we superimpose that? This is what we see here. Now, gray means not changed, independent of whether we tested it, because empirically we know for long-lived software systems, most of the bugs are in those areas that changed since the last release. We're thus not so interested in the gray areas because they haven't changed since 6 months. If they were really broken, users would probably have told us, and we probably tested them a lot of times in the past already. The interesting stuff is all the colorful code here. Green means executed during testing. Yellow is modified and not tested. Red is new and not tested. How can we interpret that? Green, hard to say. We know we executed it. We don't know how many bugs there are left. This is the fundamental limitation of testing. We can never prove the absence of bugs. But the orange and red areas are trivial to interpret because we cannot have found a single bug in there because we never executed that in any test we did. Not in the unit test, not in the end-to-end test, not in the manual test. And this picture was taken the day before the scheduled release. And when they saw that those big areas were not tested. They debugged what went wrong on a project management level, found the problem, fixed it, and then postponed the release by 3 weeks to do additional testing. And so they could fix the bugs that they found during that testing. Now, taking a step back, this is a view that's useful if you are on the role that's responsible for the entire release. But on a day-to-day work basis, it's actually often too much information, because if I'm working on a single feature or a single group of tests, I don't care about the entire system. I care about the functionality I'm currently working on. So the scope, we typically work with test gap information. And this is, again, a screenshot from our own development, is on the level of individual tickets or issues. And if I say ticket, I mean something like user story, change request, bug, epic, whatever. So something that lives in Jira or as a task in Azure DevOps work item tracking. So a description of a unit of work. And since we know the test gap information on the level of methods, and we can extract from the version history which methods were touched during the implementation of which ticket, we can lift, Ramon, yes, hopefully. That was on the test environment, but it was supposed to be shipped into production soon, and they decided to postpone that ship to production. So back to the, thank you for that comment, Ramon. Here we see the mini test gap tree map only for a single ticket. And this helps us, especially for the critical tickets, to make sure that we at least close the test gaps in those tickets. Because our experience is, especially in domains that are not regulated, where we are not forced by an outside organization to have 100% test coverage like maybe we need for an airbag or a plane. So for most areas that are not regulated, on average, we see like 50% of test gaps. 50% of the changes that are performed to software are not tested before they are shipped into production. And that's not because of lack of discipline, but that's because software is so complex and testing is so complex. And without the transparency, it's often not possible to close that. Even on the experiments we've done on our own development, we can't get the test gaps closed without explicitly looking at them. So the key idea of test gap analysis is to show us where tests are missing, to offer us a conscious decision whether we still need to do additional testing. It could be that a feature doesn't need to work for this release. Maybe there's some stuff we need for the year-end balance sheet. Maybe our business year ended in September. Now it's beginning of October. Maybe we don't need that functionality for another 11 months. And we know there's going to be another 10 releases until then. So maybe it's fine if it doesn't work. So our goal is not to have everything green as a goal in itself, but to offer a conscious decision whether we want to ship like that. So let me wrap up. We work with a lot of teams that have way more tests that they can execute in the available time. And our experience is that those test suites are often very redundant because they historically grown, have clusters of tests that do very similar things. And our conclusion is, don't always run all the tests. Instead, there are many suggestion approaches that work well in practice, that select the small subset that finds most of the bugs very quickly. And it depends on the context you work in. If it's a business information system where it's easy to capture coverage, or if it's a product line family where you want to run certain tests only on certain product variants, then maybe the test case specific coverage approaches that are termed old school are the best. In other areas, the AI-based ones, AI clustering and similarity scoring, they are much better. And I'm happy to discuss what works in your context, and I'm always open to jumping on a virtual coffee call if this is something that interests you. My last slide, if you're interested in getting the slides or getting updates from other talks I give that you can join for free, this is the QR code where you can find the slides and subscribe for the updates. Ramon, I think there was another question. Do you use a sandbox to test critical changes in our own development? Yes. Any change we do on a separate feature branch, and that branch gets tested before it gets merged into production. And in our own development, we have the guideline that there must not be any non-trivial test gaps before a branch can be merged. So the dangerous thing I said here was non-trivial test gaps. So what do I mean by this? There's some methods that are so simple that it feels overkill to write a test for them. For example, a setter that only writes a single variable to a field of the same name, or a getter that reads a single field, or a default constructor that initializes variables in a class. This is trivial functionality where you see that it does what it's supposed to. At least that's the feeling you have as a developer. And one of our PhD students actually did a paper on that during his PhD that was reverse defect prediction. And he proved that the defect density per line of code in those trivial methods is more than 1 order of magnitude smaller than in all other code. So this is why our guideline is it's okay to have those very trivial methods without a test, but everything else needs to be tested. Otherwise, the branch can't be merged. And then we still run all the tests on the sandbox, or at least all the impacted tests on the sandbox before it goes into the main branch. And there we do a lot of testing before we do releases. Ramon, thanks for the question. I hope it answered it. I think we have like 3 minutes left. Are there any further questions or comments?
There's no more questions, I see, I think. So if anyone have any question, please write down. We had, or LinkedIn had some problem to, but I look at the LinkedIn directly and there is no other questions here.
Then it sounds to me like we can close on time without running over. So we keep nobody from dinner.
Thanks so much. It was amazing. It was really very nice. It's really I enjoyed it very much. And so we're going to talk and backstage a little bit about my experiences also on that. Back 35 years ago. So let's talk about that. So thanks so much, my dear. It was a big pleasure. Okay, wait for me.
My pleasure.
Backstage. And to all of you, thanks so much for attending, and see you soon. Okay, take care.